Hello, I am Vanderlei Bagnato from University of São Paulo in Brazil. This is Bill Phillips from the National Institute of Standard and Technology in United States, and we are both members of the C2 Commission of IUPAP, a commission that promotes units and fundamental constants. In our commission, time is certainly among the quantities that we pay a lot of attention. And that will be the topic of our conversation today. Time is a necessary component in almost all physical phenomena. We basically don't have any equation where time don't play a kind of role. We don't have any kind of measurement where time is there involved in some sense. So time is important. And we all have a lot of questions about time. We want to know what's time, when did time start? We want to know, can we stop time? And we want to know how to measure well time. And those are questions that I'm going to ask Bill to start giving us his ideas about them.
Well, these are wonderful questions, and I suppose in some sense they are questions that people have asked themselves since the beginning of at least human time. And the trouble with so many of these questions is we don't have any good answers. So the question of when does time begin? A lot of people would say, well, time began at the same time that the universe began, at the time of the Big Bang. St. Augustine said exactly the same thing. He said time began with creation. But today, people are talking about what happened before the Big Bang, something I don't understand at all. Why is time always going in one direction? Many people have puzzled over this, and nobody has come up with a good answer to explain the arrow of time, as it's sometimes called. And how is it that we should understand this strange thing that is always the present, but it's soon going to become the past, and this thing we call the future will become the present? What is this strange thing that we call time? Well, among the people who asked the question, what is time, was Einstein. And the answer Einstein came up with seems a bit superficial, but in fact it's an extremely deep answer. Einstein said, time is what a clock measures. And by taking that seemingly superficial answer seriously, he changed our ideas about time.
Well, Bill, if time is what a clock measures, maybe it would be nice if you tell us what is a clock. And better even, you tell us how men learn to make better clocks as from the beginning to now.
Well, for me, a clock is something that ticks. What I mean by that is a clock is something that gives us a series of periodic phenomena that allow us to measure out whatever it is that we want to measure. Take, for example, the ancient monument of Stonehenge. This stone circle in England was apparently used by ancient people to tell the seasons, to help them with whatever perhaps religious ceremonies that they had that were connected to the seasons, perhaps things that were connected to agriculture and harvest and planting. Stonehenge apparently allowed them to tell something about the seasons. Now, why do I call that a clock? Because fundamentally it's connected to the rotation of the Earth around the sun. That's the periodic phenomenon that shows up in the action of something like Stonehenge. Of course, there's another periodic phenomenon we know about. That's the rotation of the Earth on its axis. Ancient people didn't see it that way. They saw the sun rise and set, and that periodic phenomenon was something that allowed them to measure out days. And they became more sophisticated, had things like sundials, and were able to divide a day up. Much later, Galileo made the phenomenal discovery that the swinging of a pendulum was nearly independent of how far it swings. And other people, like Christian Huygens, used that to make a pendulum clock. And that allowed us to tick off things like seconds and to connect the seconds to the day. And we understood the time of 1 second as being 1 over 24 over 60 over 60 of a day. And that came when it was possible to tick off seconds because of these mechanical clocks. And some of these mechanical clocks were wondrous in how accurate they were at the time. There was a famous prize that was offered by the British government for anyone who could make a clock that could keep time well enough on board a ship sailing from England to the West Indies in the Western Hemisphere, well enough that you could navigate within a certain distance in longitude. And this was a really hard problem, because while you could make really good clocks that stayed fixed in the laboratory or in an observatory, put that same clock on board a ship, and the ship is bouncing around, and the pendulum gets all messed up, and nobody knew how to make that clock. John Harrison devoted his entire life to making a clock that could win the longitude prize. And finally, when he was an old man, he finally solved the problem and sent his son on a trip to prove that that clock did the trick. And it did. And then that clock was used by navigators like the famous Captain Cook, James Cook, who navigated around the South Pacific using a copy of Harrison's clock. And that was one of the greatest advances in our ability to measure time. And that was in the end of the 18th century. By the time we got to the 20th century, people realized that the rotation of the Earth was not something that was constant, so that we needed a different standard of time that would be better than the rotation of the Earth. And eventually, by the middle of the 20th century, came atomic clocks. And now we had what appears to be the ultimate way of measuring time. We measure time in terms of the ticking of atoms. And the great thing about atoms is that all atoms of the same type, say cesium-133, are the same as all other atoms of that same type. And I say cesium because by international agreement, we have decided that 1 second is a certain number of cycles of the radiation that connects two particular energy levels of cesium in its ground electronic state that corresponds to a spin flip of the electron relative to the nucleus. And that's what we mean by a second today, some 9.2 billion cycles of the frequency that can drive that transition.
It seems that the necessity of man improving the precision came with the development of technology, of the way they use time. Before, they need to know the time to work and go to bed. And then they need to know the time to meet other people. And today we are in a present era where time is fundamental. Can you tell us a little bit about how the precision of time affects our present life, or of regular people in general?
You're exactly right that technology and the demands of technology have been one of the drivers in making better clocks. In Harrison's time, it was the desire for better navigation. The fact that ships were foundering on rocks and being lost and sunk because people didn't know where they were because they couldn't navigate to determining longitude. In the 20th century, it turns out that navigation again has benefited from the production of really good clocks, in this case, atomic clocks. We have today the global positioning system, the satellite navigation system, and it allows us to tell where we are, essentially any place on the face of the Earth within a few meters. We put these things on the windshields of our cars or mount them on our dashboards, and they tell us how to drive to a new place that we've never been before. Some people, I think, have forgotten how to find their way to the grocery store because they use the GPS. And this GPS system works because of atomic clocks in orbit in satellites that circle the Earth, so that at any time you can see several of these satellites from your GPS receiver, and getting signals from the atomic clocks in those GPS satellites at your receiver allows you to tell where you are.
And in telecommunication, right? The transference of data, this is an important part of modern life.
That's right. Communication that is done in a synchronous way, that is where you expect the bits of information to come in a completely regular way, is something where you need, at each end of that communication link, you need clocks that can keep track of exactly when somebody's information is coming, when someone else's information is coming. So having high-speed synchronous communication also requires good clocks. These are examples where having good clocks is driven by the needs of technology.
Yeah. Now, Bill, as we improve the precision of the clocks, it seems to me that we improve science. And as we improve science, we improve the precision of the clocks. Can you tell us a little bit about this connection?
Yes. So one example is an application in the science of astronomy, particularly radio astronomy. In order to do what's called long baseline radio interferometry, which is one of the techniques of radio astronomy for learning about distant objects and how big they are, we need two observatories that are receiving radio signals that have clocks at both ends, so that they can correlate the signals that are achieved at that are received and recorded at two different places on the face of the Earth from radio telescopes. Another application of better atomic clocks is when we use the improvements in atomic clocks as improvements in the measurement of frequency. Because whenever we're measuring time, we're also thinking about the inverse of time, which is frequency, the number of times events happen in a certain length of time. It's amazing how often the word time comes up whenever we talk about time. So frequency is the number of times a cycle of some process happens within a certain length of time, say 1 second. So once we have really good measures of time and frequency, it means that we can compare the frequencies of different kinds of oscillations in atoms. So we can look at a hydrogen atom and ask, how does the frequency corresponding to one transition compare to the frequency of another transition? And in this way, we can learn about really subtle things that are going on in the physics of a hydrogen atom. And one of the things that has happened recently is, by making very careful studies, people have learned that we don't really understand things like how big the proton is. In a hydrogen atom, we have a proton, we have an electron that is orbiting the proton, and the size of the proton affects the frequency of transitions between different atomic states. And by making very careful measurements, we've learned we don't understand the proton size as well as we thought we did before.
Wow. Controlling the motion of the atoms is an important technique to see better the atom. And you are famous for that. Can you tell us what we expect in the future with all the improvement of controlling the atomic motion we have? What could be the ultimate precision we can reach in measuring time?
Well, it's true that I've spent a lot of my career, as have a number of my colleagues, including you, trying to make atoms move more slowly. And one of the applications has been to make better atomic clocks, because when the atoms are moving more slowly, it's easier to measure them, and we can make better clocks. And today, laser-cooled atomic clocks of cesium are operating at about an accuracy of a part in 10 to the 16. That's an incredibly accurate measurement of any kind of a physical quantity. It corresponds to about 1 second in 300 million years. But that's now. The future is even more amazing. At our NIST laboratories in Boulder, Colorado, one of my colleagues, Junyi, is using laser-cooled strontium atoms held in an optical lattice, and he's measuring the frequency of a transition that's also being studied here in San Carlos, to make what is effectively an atomic clock that has an accuracy of a few parts in 10 to the 18. That corresponds to about 1 second in the age of the universe, which is about 14 billion years. Is that the end? I don't think so. There doesn't seem to be any limit to how much better we can make these clocks. It just means we have to be more and more careful about all the things that affect time. For example, when I came to NIST in 1978, a really long time ago, the very best clocks were in Boulder, Colorado, as they are today. And because of Einstein's theory of general relativity, it was known that clocks in Boulder, Colorado ran a little bit faster than if you had a similar clock near sea level in Washington, D.C., where I was. But the magnitude of the effect was about a part in 10 to the 13. And that was also about the accuracy of those clocks. So that meant that if you had a clock as good as the one they had in Boulder at the time, in Washington, it would be hard to even see the effect of general relativity, the effect of Einstein's theory of gravity on the difference between a sea level clock and a clock in Boulder, altitude, which is, you know, a mile high. It's about 1,500 kilometers above sea level. Today, Junyi's clock can see a change in height that big, 2.5 centimeters. That's how much things have changed since I first started my career at NIST. And you have to take those kinds of things into account. You have to remember how high your laboratory is compared to some other laboratory where you're comparing the two clocks. But I don't see anything fundamental that says we can't keep going.
Wow. You see, time is an important issue, and we are proud to be part of a commission that makes sure science and scientists are worried and advancing so much the frontier of the knowledge by measuring time better.